Let us start. Welcome to this session on probabilistic programming, and we will start with a talk on optimizing density computation in probabilistic programs via automatic loop vectorization by Hyoungjin Lim. So thank you.
Okay. Hello, my name is Hyoungjin Lim, and I will present about our paper named Optimizing Density Computations in Probabilistic Programs via automatic loop vectorizations. So let's start with the motivation of our paper. So in probabilistic inference, calculating density from a given sample is one of the most essential operations, which is repeatedly calculated with the inference process and therefore occupies a huge portion in the total inference time. So on the other hand, in probabilistic programming, which aims to automate probabilistic inference, density is also calculated automatically by executing probabilistic programs under density computing semantics. Let's see the examples. Here is the probabilistic model P expressed as a program. Then, if we need to calculate the log density of the model P with a given sample G, probabilistic programming framework executes model P in the density computing semantics, which calculates an intermediate densities for each sub-comment and returns the summations of all intermediate densities after the execution. So this calculation based on standard execution is simple and intuitive. However, it can be screwed up if a probabilistic model contains a long loops. Usually, loops appear in a model to iterate over dataset or describe time series model. And therefore, probabilistic models in real world are likely to have long loops in their models to handle huge data sets or describe long time series data. The problem is, in standard executions, for loops with length n are executed sequentially so that they take O(n) times for n length loops. And if we use this standard execution in density calculations for real-world models, density calculations would become costly, and it leads to the slow inference. Therefore, it is essential to vectorize loops in probabilistic models in real-world application. However, if a user tries to vectorize the for loops in their model, there are not much options to choose. So at first, there are only a few vectorization tools for the for loops. And each of those tools is applicable to a narrow range of loops which satisfy very strict conditions. And if the tool is used in loops which do not satisfy that condition, the calculation becomes incorrect. In this paper, we propose the novel vectorization method, which is applicable to any kinds of for loops with some advantages. First, our method guarantees correctness for any applications to loops. And second, our method is easy to implement in any tensor-based framework. And last, our method shows comparable results to other existing methods. So let's move on to the main idea of our paper. So before the main idea, let's check what language we use for log density calculations. So actually, we just use a standard imperative probabilistic program language. But we exclude while statements in our language. But I think it's still expressive to describe real-world probabilistic models. But during the rest of the presentations, instead of mathematical notation, I will use diagrams to depict the semantics of the commands. So actually, it looks like this. So for the command in imperative processing language, the semantics gets two inputs, which one is input state and another one is given samples. And then the semantics outputs two results consisting of the output state and log density. For examples, if we execute sample command over state S with a given sample, then the result will consist of an updated S, where X is assigned to 3.2 according to the given sample, and the log density of a given sample 3.2 from the normal distribution. And moreover, since a given sample is always fixed during the full execution of the program, I will omit the diagram for the samples for depicting our ideas. Okay, then let's start with the standard execution for a for loops. So in standard executions, we try to calculate the output of for loops executed over the input state S. And to calculate this, in standard executions, calculate the intermediate states and densities, which is essential to calculate the final result. So at first, start with initial state S. We obtained S0 and R0 by executing the sequence of commands consisting of assignment statement for I and body loop C. And then by using this S0, we obtained S1 by using the similar body loop. And we iterate these procedures until we get n intermediate states and n intermediate densities. And after that, we calculate the final states by just picking the last intermediate state. And then the final densities will be the summation of our intermediate densities. Then how our method work? So in our method, we optimize these loops by parallel executions. So at the goal of the execution is same. We want to get the final result by executing for loops in initial state S. But our method execute these parallelized commands are a little bit different from the standard executions. First, we will start with the initial state S, and our method makes n+1 copies of the initial state S, and then group them into a tuple of n+1 states with indices from -1 to n-1. And then our method constructs a special operator for a tuple called C parallel. This C parallel has two distinctive characteristics, and the one is it consisting of element-wise operations, and therefore it can compute in constant time with n processors. So, in the form of in a type of C parallel, C parallel gets a tuple of n+1 states as an input, and then outputs a new tuple of n+1 states. And additionally, it outputs a tuple of n densities, which are paired with states with indices 0 to n-1. And let's go back to U0. In U0, our method applies C parallel into U0 and gets a new tuple U1 with a new tuple of n densities. And then we just repeatedly apply the C parallel into each output. And if we repeat this procedure, at some point we reach the stopping point UK, where every state and output densities looks like this, and it means UK contains every necessary information to calculate the final output for the for loops. And then we stop the iterations of application of C parallel, and then just calculate the final result and returns it as an output. So this full procedures takes OK times with n processors, since C parallel can be done in constant time with n processors. At this point, I think you might have two questions about this procedure. So one is how actually C parallel works, and the second is how can we detect UK contains the necessary information. Let's look into those questions one by one. So first, I will depict how C parallel works by simulating the first iteration and second iterations. So in first iterations, we will start with U0, and C parallel first shift these input states, which means for each state with indices between 0 and n-1, the C parallel overlap those indices by the states with the previous indices. So for the first iterations, since every states are same to S, there is no difference between the shift to U0 and U0. And after that, C parallel makes a command for each state with indices between 0 and n-1 as follows, and then just execute these commands for each corresponding state, and using this, and then use the results to construct the output tuple U1. So before moving on to the second iterations, you can see that the states and densities, the output states and densities in index 0 already contains the intermediate states and intermediate densities appeared in the standard execution. And if we iterate these applications over U1 again, then we can see that now U2 contains two intermediate states and two intermediate densities in the standard executions. So we can see the patterns. U1 has one intermediate state. U2 has two intermediate states. Then we can deduce that if we iterate this procedure n times and gets un, then this un will contain every necessary intermediate states and intermediate densities in the result. So, so if we go back to the procedure I initially depict, we can say that at most n times of iterations, our algorithms can be stopped. However, can we detect the situation that UK with k smaller than n already satisfy the stop condition? The answer is yes, and our method detect this situation by comparing the current output and the previous output. So for examples, let's assume that we already iterate the procedures k times and found that the result of the k iterations is same to the result tuple in the previous steps. Then from these informations, we can deduce that UK plus 1 will be same to the result in the UK, both in states and both in densities. And this can be extended inductively until UN. And then in conclusion, we can know that UK, the value of UK is same to the UN, which is just the necessary information for every intermediate states and densities. And it means we can stop the iterations at this point and calculate the final outputs for comments. So the whole I depict the whole procedure, and we implement these whole procedures by using tensors. So we implement optimized execution by using PyTorch tensors, and we can get a powerful support of GPU operations. And then we integrate these systems into the Pyro framework, which is one of the popular PPL frameworks, and evaluate our methods based on this implementation. So in the evaluations, we try to answer two questions. So one is how our method is applicable to a broad class of models. And the question two is about the performance. So is our method faster than other existing methods? So to answer these questions, we compare our method with two baselines and with 8 benchmarks. So for the question one, we compare the applicability between three possible methods for vectorization. And as shown in the table, we can achieve vectorizations for every 8 benchmarks, but the two alternatives miss some of the benchmarks. And especially for discrete HMM, it is so specialized to a certain models, so it is only applicable to only 2 benchmarks. And then among those benchmarks, we compare the inference time between those existing methods. And then the results show that for V-Markov, we dominates the method in every benchmark. But in discrete HMM, we cannot achieve the better performance. It is because discrete HMM is so specialized and ignores many overhead occurred by the PPL framework. And in additionally, there is a the table only shows five benchmarks because the rest of the three benchmarks we can so our method is only one possible vectorization tool, which is applicable to the other three benchmarks. Okay, so since this is just the description for our method one by one, I just decided to skip the conclusions. And if you have an interest in our papers, please tell me or talk it in the coffee break. Okay, thank you.
A question, remark? So I have a first question. So you said that you don't consider while programs, while loops, but is it difficult to generalize to while loops? I mean, you have to choose arbitrary n that is given, the parameter that is given with respect to the processor that you can run in parallel. And then does it work, your optimization? Does it work easily, or there are some issues?
Yes, thank you for the questions. So actually, Sangho and I also considered the extension of our method to while loops. And I think it can be possible if we can dynamically allocate the processors. If we fail to reach the halting conditions within some processors, within some fixed processors. And in that case, we can double the number of the processors. So, and then we can check it. Yes, it achieves the halting conditions and so on. So,
okay, thank you.
So on the benchmarks, there were the other ones where their methods aren't applicable, but could you compare against the unoptimized baseline? How much speed up do you get? Like even if you can't compare against other optimizations, do you have a sense of how much performance improvement you get?
Okay, I'm sorry, I have to turn on the computer again. So, could you repeat your question again?
Yeah, so for the 3 examples that the other optimizations don't apply to,
yes,
you could still compare your method against the unoptimized baseline.
Yes.
Do you have a sense of how much improvement you get?
So I think I can show the full result of our experiment. So this is a full description of our Yes. So this is the full result of our experiment. So we also use unoptimized method, which we depict as depict in sequential. And you could check that the sequential is not comparable to any other vectorization tools. And if you see the ARM and TCM and HMMs, then you could see that like our method is like maybe like 100%, 100 times better than the sequential part. So.
Okay, so we can thanks the speaker again.